So, welcome to Nonlinear Optics. I had to turn up the volume, otherwise it would have been a problem. Actually, we got a new beamer here, and therefore the sound doesn't work. So when you write, I don't necessarily get a signal that a comment arrived. Yeah, very nice new beamer. Much brighter than the original one, much higher resolution, perfect for hybrid teaching. In other words, completely useless for the time being. Well, also the Christmas tree disappeared, as you see. But let's get serious. There were a few questions, mainly concerning the final. I wrote you an email with a proposal on how to arrange it, how to conduct it. I hope everybody is happy with that. So far I didn't get objections to it. Or what I would even prefer, suggestions for better ideas. The question here on the chat has been about registration for the final and that there's a deadline by the university. Well, the point is my deadlines are more relaxed than the ones of the university. The idea has been that we respond to your emails and confirm that we got it. I see now that that one apparently has not been answered, so I will check on that. And there's now another question: can we take a collection of formulas with us to the exam? Yes, I guess this should be, yeah, so a collection of formulas, say one page should be okay. Yeah. Okay, so with this, let's continue. What we talked about last time was actually phase matching, and we'll continue on that today. So the last few things that we discussed were type 1 and type 2 phase matching. And you might remember that we had a particular interesting example for the difference between type 1 and type 2 phase matching for parametric down conversion, spontaneous parametric down conversion. So type 2 parametric down conversion is a particularly important source for quantum cryptography, informatics, computation, and so on. So I distinguish between type 1 and type 2, but there are people who distinguish many other types of phase matching. In my career so far, I hardly encountered any of these, but for the sake of completeness, I copied that. I guess I stole that from Wikipedia. The other thing that we did, or the main topic actually, had been critical phase matching, or phase matching by angle tuning. Yeah, so these are the same, describe the same thing. And as opposed to non-critical phase matching, and today we'll learn to know another type of phase matching. But non-critical phase matching, this is the case where you actually where the k-vector of your beams are actually parallel to the semi-axis of the indicatrix, and this is of course of advantage, as we'll see. Well, you can probably already imagine what could happen for the different polarizations of, say, the second harmonic and the fundamental, if both see a different refractive index, and if the angle is so relative to the semi-axis of the indicatrix is not equal to 0, then of course there will be, well, the effect of birefringence, namely that you see two pictures, or in our case, that the beam will be split, and this would mean that the waves that are supposed to interact are spatially separated, and this is of course a problem. It's called Walkoff, and as I said, we'll consider it in a few minutes. Well, all of these, so the the spatial Walkoff problem is not present in for non-critical phase matching. There, the idea is to tune the refractive indices, for example, by temperature. So, and this we discussed last time, and I have shown this figure in a little bit nicer version. Yeah, so separate for the two wavelengths regions. Yeah, so look, there are two axes here, and one corresponds here. Yeah, so the steeper curves correspond, of course, to the shorter wavelengths, and this one here, for example, to this wavelengths, and where these curves overlap, you can in principle have phase matching. Okay, so this was non-critical phase matching, and the next thing that we would look upon would be the tuning curves and the bandwidth for phase matching. Right, so we have seen, well, we know, of course, that all the refractive indices depend on the wavelengths, and we've seen that the phase matching angle also so the phase matching angle depends on the refractive index and thus also on the wavelengths. And therefore, the question is, of course, how critical is this? So if I deviate with my wavelengths a little bit, or even worse, if I have a short pulse with a broad bandwidth, how is this with the bandwidth of phase matching? And yeah, so we'll look at this in the following. So this is chapter 7.5, tuning curves and phase matching bandwidth. And we start with a natural definition of phase matching efficiency. And later we'll plot this efficiency as a function of wavelengths and of phase matching angle, so of the angle of the crystal with respect to the beam. So let's start. So a natural definition of phase matching efficiency is, of course, the ratio of what you get out divided by what you put in. So we call this eta, is usually for an efficiency, and this is the intensity that we have with a certain phase mismatch divided by the intensity where the phase mismatch would be equal to 0. And we have learned in chapter 3, this was equation, yeah, this was chapter 3.4. So we have learned that this obeys the sinc function squared of delta k times L. L is the length of the crystal, of the nonlinear medium, divided by 2. Yeah, and we got this sinc function when we discussed solutions of the coupled wave equations for the approximation that the pumps are undepleted. So, and starting from this, we will define the bandwidth, the phase matching bandwidth. So the phase matching bandwidth can be defined by the condition that eta of a certain delta k 1/2 is equal to 1/2. Yeah, so we take the full width half maximum of this sinc function. This is what is written here. Now, what we can do is to try to visualize this bandwidth by just plotting the sinc function as a function of the parameters of interest. In the case of critical phase matching, the parameters of interest are the wavelengths and the angle of the crystal with respect to the beam. And okay, yeah, so this doesn't work here, yeah. Yeah. So there were a lot of comments, and I was talking and talking. Yeah, so fortunately, you came and made me aware of the problem. So what we could do is that no, I don't want to give my phone number on the internet. Okay, but anyway. I hope I concentrate better so that this works now. So let me quickly, another comment?
Still off.
What is off?
They have that hierarchy part, still off.
Still off. Why this? Oh, it doesn't seem to work. Now it's on. But it's gone again. Okay, so now it works. Oh yeah, I have to pay attention to that today. So I hope things work now. Let me just go through quickly to what we had. So we define the phase matching efficiency, right? And we define it in a quite natural way, namely the intensity with a certain phase mismatch, with a finite phase mismatch, and here divided through the intensity where the phase mismatch is equal to 0. And this is the sinc function, and we got it somewhere in chapter 3.4, as I said. And next we define the bandwidth, and the bandwidth is where the efficiency has dropped to 1/2. Yeah? And the next thing that we would do is to plot this function. So the bandwidth can be visualized by plotting this sinc function, sinc squared function to be precise, delta k times L divided by 2 is a function of the relevant parameters. Yeah. And this could be theta and lambda for critical phase matching, or temperature and lambda for non-critical phase matching. Well, and if there are other ways of phase matching under certain circumstances, say pressure, something, yeah, then you would put these numbers here. One thing that is already clear is that the phase matching, so the phase matching bandwidth is the smaller, the larger the length. And you see this, of course, immediately, well, say here, because it's the product of delta K and delta L, right? So you can make delta K a little bit smaller and then afford a bigger length. Or if you need a bigger length because of, say, efficiency consideration, then you have to live with the fact that your phase matching bandwidth gets smaller. So it is evident that the bandwidth is the narrower the larger the length. The length L of the crystal. Yeah, in fact, it is inversely proportional. Yeah? So, in fact, inversely proportional. So next we consider a specific example, and the most important in nonlinear optics is always second harmonic generation. So we look at second harmonic generation in EEO configuration. So type 1 phase matching. This would be a positive birefringent crystal. So EE means extraordinary, extraordinary. So the two, so the fundamental in this case, so the fundamental is extraordinary, and the second harmonic is the ordinary polarization. So let's write that down. For collinear second harmonic generation in EEO configuration, we would plot, this is what we said that we plan to do. We would plot delta K, and the sink, of course. So we would not yet plot, so we would use as delta K. We would use delta K of lambda and theta, and this would is by definition 2 pi, and then minus 2 the extraordinary index of refraction plus the ordinary index of refraction of half the wavelengths. So no theta here because it's ordinary, the ordinary polarization. So this is by definition the phase mismatch for second harmonic generation. Well, now the only thing that we need to do is to find values for the refractive index. And in order to do this, you look up the Sellmeier equations. So the Sellmeier equations are a few parameters that describe very accurately in a certain range of wavelengths. They describe very accurately the refractive index, typically to 3, 4, or even 5 digits, depending on how many terms, correction terms, are included. So we would use this thing here. This means that the only thing needed are the Selmayr equations. For the crystal under consideration. For the crystal used. Yeah, and of course, if you do temperature tuning, then you would need the Selmayr equations where the temperature is included. So we look at an example, namely at second harmonic generation using KdP. Yeah, a very frequently used nonlinear crystal, particularly in the near infrared. So people can grow very large crystals of that. So for the NIF laser facility, they use crystals of this size or so, and hundreds of them, in order to generate, I think, the third harmonic. But as an example, KdP for second harmonic generation. And just that you see, an example, I write down this Selmayr equation for this example. I found it on the web page of a company. Actually, I have many Selmayr equations of many types of glasses and crystals on my computer, and perhaps you should try to establish something similar. So therefore, it's quite easy for me using Python or Mathematica or something in order to plot what we are going to plot. So in this case, this would be 2.259279 plus 13.00522 lambda squared divided by lambda squared minus 400 plus 0.0100896 divided by lambda squared minus 0.0129426 something like that. Yeah? So this is the typical structure of the Selmayr equations, and it is of course assumed that you plug in the wavelengths in a unit agreed upon, and for the Selmayr equations it's typically micrometers. Yeah, so if you plug in here lambda in micrometers, then you would get the dependence of the ordinary index of refraction on the wavelengths with a very high accuracy. And there's a similar formula for the other direction of this uniaxial, positively birefringent crystal. I'm not going to write it down. It looks similar, yeah? But just that you have seen how such Selmayr equations look like. As I said, this one I just got from a web page of a company. So next we plot this. So next we plot the sinc function as a function of delta k times L divided by 2. So next we plot sinc squared of delta k times L divided by 2. And it looks like the following. Yeah, and this figure here actually says a lot of things, as you might guess. Yeah, so the blue areas is where the efficiency is basically 0. And where it's bright yellow, this is where the efficiency is close to 1, or equal to 1. If you look very carefully, I'm not sure whether you can see this on YouTube. Let me check here. Probably you can see it if you look very carefully. Then you see here parallel stripes to this bright yellow stripe, right? And these are just the side wings of the sinc function. So you see here that I indeed just plotted the sinc function as a function of wavelengths. This should be written down here, right? As a function of wavelengths in micrometers here. And here this angle theta. And now it's clear that if you choose a certain wavelength, say 800 nanometers, you can immediately read off the phase matching angle, but we derived already a formula for that, which gives it directly. But what you also see is the bandwidth. And now it depends on which wavelengths and which wavelengths you have chosen. It is clear that if you take 600, say 650 nanometers, something like that, then the bandwidth is very narrow. On the other hand, close to the minimum here, it is of course very broad. So if you have here a wavelength of a little bit more than 1 micrometer, say a typical wavelength of an iridium YAG laser or so, 1064 nanometers, then we would be pretty much here, and there the bandwidth of for phase matching would be quite large. So so yellow colors indicate efficiency close to 1. Blue, for blue eta, so the efficiency is close to 0. Yep. And this yellow curve is the tuning curve. Yeah? So the yellow curve is the tuning curve. It provides the phase matching angle and the phase matching bandwidth. And you can do this game with any other material also, if you know the Sellmeier equation. Let's do another example, namely a difference frequency generation. So another example. So these to be able to plot these tuning curves, this is actually quite important. So therefore, another example might be justified. Difference frequency generation in this time OOE configuration. Remember, the last one, in this case E, this is the big photon, the biggest photon, the so-called pump. And then what we have for delta K is a function of lambda 3, lambda 2, and zeta. Of course, lambda 1 then is given by the condition that omega 1 plus omega 2 is equal to omega 3. So in this case, we would have then 2 pi minus NO of lambda 1 divided by lambda 1 minus NO of lambda 2 divided by lambda 2 plus the extraordinary index of refraction, which of course also depends on the orientation of the crystal, on theta. So we would have this equation. Now we have three variables, and what we typically would do is to say, well, we pump it with a certain frequency, and therefore we consider this fixed. In our case, this would be lambda 2 is equal to 1064 nanometers. This is for which I made the example. Yeah. In a given situation, in a given problem, one of the wavelengths is fixed anyway. In a given problem, in most given problems, say here lambda 2 is equal to 1064 nanometers, right? And then I did the same thing. I looked up the Sellmeier equations and I plotted the efficiency, basically the sinc function. So, and this is actually for lithium niobate. Yeah, so the example here, the plot was made for lithium niobate. We'll talk about lithium niobate again later, because it is a particularly interesting crystal. So far, or so much to the tuning curves and the bandwidth of phase matching. Of course, what one could do would be to derive a formula here for this width here, right? But I'm too lazy to do that. So the next thing is what I already indicated, namely the problem with the walk-off. Problem with walk-off. So let me show here, let me show quickly some nice photos somebody made for Wikipedia. It is referenced here, of course. And what you see here is, I think it's calcite, and they use a blue laser beam here. The nice thing is that it not only experiences birefringence, but also there's also fluorescence, such that you nicely see the beam inside the calcite crystal. So it seems that you see 4 of these beams. Well, remember, there's birefringence, you see everything twice. But nevertheless, this beam here, the 2 polarizations of this beam, they are split such that you get out 2 beams. And now you can imagine if you would try to do in this crystal Actually, I don't know the crystal symmetry, but I guess second harmonic generation is not possible in calcit. But if you would do in such a crystal, if you would want to try for nonlinear process, say in this case third order or something, then you see that these beams, get separated they get spatially separated. And then we assumed in our coupled wave equations that they are all present in the same place. Yeah? So that the amplitude is reduced here. So the overlap is not given. So and this is obviously a problem that will affect actually two things, namely, as I explained already, efficiency. But the other thing is that it will also distort the beam profile of the product beam. Yeah, so if you want to generate here the second harmonic, then you have to be aware that the second harmonic beam can or will be quite distorted here, because what is generated here in this overlap region makes it to this point here, but what is generated here would end up here in between these two beams. Yeah, so you see that you don't get, so you would expect an elongated beam profile in this case. So we are at chapter 7.6, walk-off. And the first point would be the spatial walk-off. We'll also come to temporal walk-off. But let's first discuss spatial walk-off. So walk-off. And we start with spatial walk-off. So like this. So birefringence causes a lateral walk-off. Between the interacting beams. And the reason we explained at the very beginning in chapter 1, where we noticed that the propagation direction is not necessarily the same than the direction of energy flow. In other words, the wave vector is not necessarily parallel to the Poynting vector. This is basically the reason for this effect of birefringence. So the reason is that wave vector k and Poynting vector s are not parallel if k is not parallel to one of the semi-axes. Yeah, of course, for the extraordinary polarization. Now, the angle, and I call it rho, between both what I mean is actually between ordinary and extraordinary beam is given by formula that you can look up in optics, linear optics. So what we see is that it depends on the derivative of the refractive index with respect to theta. Yeah, so the stronger the birefringence, we'll see the stronger this Walkoff problem. Yeah? This is of course clear. So the resulting separation between the interacting beams again. Okay, sorry for that. So the resulting separation between the interacting beams, I'm just writing what I explained. Reduce the mixing efficiency yeah. So let me look at here. Okay, so it should be okay now, as far as I see. The resulting separation between the interacting beams reduce the mixing efficiency and distort the beam profile of the product beam yeah, and there's a one-to-one correspondence between the final phase matching bandwidth and the Walkoff phenomenon. There is a one-to-one correspondence between phase matching bandwidth and Walkoff. Yeah? So in the regions where you have a strong, where you have a small bandwidth, yeah, because this this curve is steep, there the Walkoff problem is typically is also pronounced. Yeah? Okay. Well, what are our options to reduce the Walkoff problem? Well, the first thing that you could think of is to increase the intensity right? If you increase the intensity, then frequency conversion is more efficient, and then you can afford a shorter crystal, and therefore the Walkoff problem is reduced. The intensity can be increased by, well, focusing harder on the one hand, and by increasing the power, by making shorter pulses, or if you have enough money, by buying a bigger laser. Unfortunately, the easy way, namely just to focus harder, doesn't work, because if you focus harder, then your divergence gets higher, and also your focus is smaller, so the overlap problem is more severe there. So the only option in this sense is actually to increase the power by using shorter pulses or more pulse energy. So Walkoff can be reduced by increasing the nonlinear conversion efficiency by increasing the intensity. However, increasing the intensity E, so increasing E by focusing harder, does not work. Because this would increase divergence and decrease the focal size. So implying that the overlap problem is more severe. I just did an example for that. So I looked at KDP, the same example that we looked at above here when we looked for critical phase matching, so many pages back here. I think it was here. Right? So example KDP, I took a wavelength of 693. I'm not sure why I chose 693. I guess I just checked some result in some book and verified the calculation there. So I take 693. I calculated the phase matching angle of 53.7 degrees, and for the same, so using the same, so I used, of course, the Selmayr equations also there. So using the Selmayr equations, I can calculate the derivative of the refractive index with respect to theta, and from this I can calculate rho. And what one finds for birefringent crystals is typically a few tenths of a milliradian. So example, KDP at 693 nanometers, and from this we get rho is equal to 0.18 milliradian. Looks very small, but actually can make a problem. The next thing is temporal walk-off. So there we assume actually that we use short pulses, and then the idea is that the group velocity for the short fundamental pulse, so say a femtosecond pulse at 800 nanometers, that this pulse sees a different group velocity than the second harmonic, which also may be a femtosecond pulse of, say, 50 femtoseconds length. And because the dispersion curve looks different there, also the group velocity looks different. Right? And therefore, after a certain distance, both pulses, which at the entrance phase overlapped, well, as they move through the crystal, they have different group velocity, and therefore they detach from each other. Well, of course, the fundamental pulse will always produce more. Well, actually, this should be the fundamental pulse. It will always produce a second harmonic, which means that the second harmonic will also get stretched out. In the same way as the beam profile was distorted, here the pulse shape will be distorted. Good. So temporal Walkoff. For short pulses, analogous problems arise in time domain. And the reason is that there is a different group velocity, because the group velocity Vg, which is defined as the omega over dk, and you can calculate so what was this here? So there's obviously a misprint here in my notes. I don't have this here. This should be. So this is it should be equal to C over n minus lambda dn over d lambda. I think this is the correct formula. So the group velocity, this will be different for the ordinary and for the extraordinary polarization. Is in general different for ordinary and extraordinary polarization. That would have been a good opportunity to make a short break, so of 5 minutes or so. So see you in 5 minutes. Of course, if you have comments, you can write them in the chat and I will answer them afterwards. Yeah, let's continue. There were 2 questions as far as I've seen here, pretty much about the same thing, namely the Zoom meeting, whether there will be one at 5 o'clock this afternoon. Last time there weren't many who attended, but I will offer it again, and well, we'll see how it develops. The other question has been that this link was not available to some. I put it on Moodle. I may have forgotten to also send an email for your convenience, but this is the usual repository where you find information for this lecture. So I will again put it on Moodle after this lecture. I'll create one, and then you can see me on Zoom at 5 o'clock. And of course, I would appreciate if some of you join, and I would also appreciate if you would switch on your camera. Otherwise, it's a little bit annoying That's annoying enough here to give this lecture in this form. So let's continue with walk-off. So temporal walk-off. I explained quickly what it is, and I just repeat it. So we have the fundamental. Say for second harmonic generation, the fundamental is of course the smaller photon, so the refractive index is smaller, and it produces a second harmonic, so another pulse that typically has, well, it certainly has a smaller phase velocity. For the group velocity, it depends, of course, on the this derivative here. Yeah, and then we can start and calculate the difference between the maxima of the pulse. So this is what we do next. We calculate the spatial separation and call it delta Z of the pulse maxima. In propagation distance, and then we get delta Z equal to the group velocity of, say, the fundamental minus the group velocity of the second harmonic times t. And so this is the propagation time. And then if this delta Z is larger than the pulse length, the spatial pulse length, so c times tau, so if tau is the pulse duration and c is the speed of light, then the length of the pulse is c times tau. So if this is the case, then both pulses would be separated. So this is the order, this gives you the order of the problem. So this is a method to estimate whether you have a temporal walk-off problem. So once delta Z is larger than the pulse length, the spatial pulse length, c times tau, the product pulse is separated from the driving pulses, or in the case of second harmonic generation, just the driving pulse. Now, this means that t is equal to difference, and from this So, do you hear me again? Yes, okay. At least I realized immediately that that something is going on the chat. Seems that I'm learning. I got it already. Thank you. You. Okay. So I think I have to explain again the idea of this compensation. So how to compensate, for example, for temporal walk-off. You would use several crystals, birefringent crystals in series. In the first one, you would start to create the second harmonic, say, and then you would use another birefringent crystal that is oriented such that it doesn't produce nonlinear effects. You orient it such that it puts together both pulses again. And if you are clever enough, then you can even design configurations such that spatial and temporal walk-off is compensated. So compensation, do I need to write this down? Yes, I write it down because I have a reference for that where you might want to look it up if you need it at a later point. So in principle, both effects can be compensated by sequences of crystals where crystals with nonlinear interaction alternate with crystals that compensate walk-off. The walk-off created by the nonlinear crystals, of course. Yeah? And as a reference here, a paper from Optics Letters, more than 20 years old. Yeah, but these things are not standard because this is cumbersome, such systems. Okay, let's come to the last subchapter of this chapter here, namely quasi-phase matching. So I mentioned that we have critical phase matching, we have non-critical phase matching, and increasingly important these days, there is also quasi-phase matching. So what we have seen so far is actually that critical phase matching is the most versatile type of phase matching, and indeed it is what is mostly used. But there are situations where critical phase matching, where angle tuning is not possible. So quasi-phase matching QPM This is the abbreviation that you see frequently for that, QPM, quasi-phase matching. Well, what are the situations where you can't do bireferences, so critical phase matching? There are a few of them. So the first one would be that you have an interesting nonlinear medium, say gallium arsenide, but that this damped crystal is not bireferenced. Then you have a problem. The other class of problems is when you want to go to the UV. So you know that as we go to the UV, the refractive index steeply increases. But in bireferential crystals, the difference between the refractive indices, between the ordinary and the extraordinary refractive index, remains fairly constant. And therefore, you are out of luck for at short wavelengths. So there are, where critical, so this is just what I'm trying to explain. So two reasons where critical phase matching is difficult. I mentioned last time this Chinese scientist who invented a lot of nonlinear crystals, very important nonlinear crystals, the most prominent perhaps being BBO. And then there was this other one, KTTP or something like that. And this crystal is, he worked for more than a decade, I think, on growing this crystal, and this is particularly important because one can produce, because it works for very short wavelengths. I'm not sure what the ordinary and extraordinary refractive. I don't have the Selmayr coefficients for that crystal. Otherwise, I would have looked it up. So I'm not sure how it is phase matched. But anyway, so these are two issues, and then there's a third one, namely, sometimes you want to use the D33 nonlinear coefficient. So remember, we have a third rank tensor in order to describe the nonlinear susceptibility. And there is this component chi333, and in contracted notation it is D33. We talked about that in the first chapter. And now, if you have this chi333, then it's clear that it addresses or that it couples only the waves with the index 3, so only the same polarization, right? So if you want to use D33, then bireferential phase matching is also not an option. And, well, kind of Murphy's Law, you know, the D33 nonlinear coefficient usually is the most interesting because it's the largest one. Okay, so if this is the problem, then you need another solution. But before we look for this other solution, we quickly write that up. Yes, so critical phase matching is not always an option. And 3 examples. So the nonlinear crystal is not bireferenced. the other was in the UV, the birefringence is often not sufficient and the third one is if you want or need to use the D33 nonlinear coefficient, all the waves must have the same polarization. So birefringence also wouldn't work. Yeah? So, and if this is the case, then you have to do quasi-phase matching. Let me try to show this here quickly, and I guess I show it here on the view graphs that I have prepared. So like this. Yeah, so what you see here is supposed to be a nonlinear crystal, and what you see is the fundamental, and you see the second harmonic, and it's certainly difficult to see, but you see that they have the same phase all the time. Right? In the beginning it's not easy to see, but this is also starts like a sine, just the amplitude grows because, well, because we create the second harmonic. If this is the case, then we are perfectly phase matched, yeah? Then there's no problem. We just would add another piece of crystal and the second harmonic would grow until it starts to deplete the fundamental, and you could have 100% of efficiency. Well, this is not the situation or the problem that we want to deal with. So what you see here is the same, almost the same thing, but you see that the phase here is different. Yeah? So whereas this here ends with a zero transition for the field at the exit phase of the crystal, the second harmonic has its maximum there. Yeah, so it accumulated a phase difference of a quarter of a wavelength. Right? And then if you would continue in the same way, yeah, so you see I continue here just in the same way, then the amplitude would decrease again. Yeah, so we know this, this problem, of course. So what can we do? So we have this situation, and now the idea is to just put, say, a piece of glass of appropriate length that does no nonlinear effect, but just affords that both the phases of both waves match again. Yeah, so as shown here. Yeah, so in green you have this different piece of material, and you see that well, that at the end of this piece of glass we start with a zero transition here from below, right, from negative to positive, and the same thing here, just like here, right? And then if I would add this piece of crystal here, if I add this here, then it also grows, right? So this is quasi-phase matching, right? And of course, after here at the exit phase, we have the problem again. But we could take another copy of that piece of glass and put it behind and stack this nonlinear element discretely together. There's a problem with it. We have done a quick calculation a while ago where we saw that the coherence length and thus the lengths of these slices of crystal must be is very small, in the order of a few micrometers. I think the number we calculated was 5 micrometers or so. So it will be very difficult, if not impossible, to produce this here. But under certain circumstances, so high harmonic generation in gases or so, this idea here is actually an option. There is another possibility that you could use, namely, what you could do, and this is now indicated here with these light gray arrows, what you could do is to put one crystal like that and the other crystal like that, such that the sign of the nonlinear coefficient changes between these slices of crystal, right? And then you wouldn't need these pieces of glass, so you would use the same material, just oriented in the opposite direction, and and you could stack many of these together. But of course, the technical problem, namely of producing that, is the same. Okay, anyway, let's write up this idea of quasi-phase matching. And actually, the idea of quasi-phase matching is very old. It's probably, I guess it's older, probably old, so older than angle tuning. It goes back to the very beginning of nonlinear optics in the early 1960s. So we take a few notes on that. So in this or these situations, quasi-phase matching is the remaining option. So the idea is to make the nonlinear medium not longer than the coherence length, 2 divided by delta k. And afterwards, both waves are sent through a medium typically without nonlinear interaction, without nonlinear interaction. Through a medium without nonlinear action, but of a length such that both waves are in phase again. And the same thing is to switch the sign. So if the third problem here, D3, 3 is the problem, you could switch the sign of the nonlinear coefficient, maybe in this case D33. The other option is to switch the sign of the nonlinear coefficient. Again, by slicing the crystal and putting the slices together in reversed orientation. But there is a third option. Yeah, so all of that is not very practical, and therefore for 30 years not much happened with quasi-phase matching in reversed orientation. Yeah, so all of these ideas are not very practicable. Because L coherence is in the order of a few micrometers. So now the approach that does work. And the most prominent example is lithium niobate. And lithium niobate, you see here the crystal structure. Lithium niobate is a ferroelectric material. By applying a very strong electric field, you can align all the dipoles. So every unit cell is a little dipole. And now if they all have the same direction, then there is, well, more or less macroscopic dipole moment. At least you have a uniform dipole moment. And this already is the idea, right? Here you see this, the structure. And if you look very closely, so here there's no polarization, but here if they are polarized, then the positions of the niobium atoms is a little bit shifted. For all the niobium atoms in the same direction, and because of the different electron affinity of the niobium as compared to lithium and oxygen. This gives then a permanent dipole moment. And it can be switched by a strong electric field. Actually, a very strong electric field, namely more than 20 kilovolts per millimeter. Here you see the same thing in the cross-section. So these dashes, these black lines here, these are the oxygen layers. And again, so here you see niobium and lithium. And depending on where they sit in the vicinity of the oxygen layers, one has the plus C orientation or the minus C orientation. So the only thing that you have to do is to pole lithium niobate, and actually to periodically pole it. And this is done in the following way. So here I have stolen a few slides from a colleague in the US. So what you would do is that you take a slab of lithium niobate, and then lithographically one would deposit electrodes on one side, so structured electrodes, kind of a grading, and another electrode on the other side, and then you apply, so if your slab is a millimeter thick, then you would apply 20 kilovolts to these electrodes. Well, the problem is, of course, breakthrough, and there has been a lot of research and investigation on how to avoid breakthrough and nevertheless get regular structures of alternate polarity of these domains. And after many years of research, people finally managed how to do it. And well, this here is a phase contrast image of periodically poled lithium niobate. This is how people abbreviate it. Some say just piplin, yeah, to this material. Okay, and then phase matching, of course, goes in this way, right? So I could have shown this curve earlier, of course. So this applies for all quasi-phase matching, so that this here is the goal, right? If this here is not possible, then this here is the next best solution. Actually, this periodically poling of a crystal, this offers a lot of flexibility for phase matching. It is technically demanding, yes, but what you now could do is to use to pole them not in a strictly periodic way, but to change the lengths of the slices. This is then called chirped quasi-phase matching. Yeah, so this is another a slide I stole from a Swiss colleague at the ETH. And what you can then do is to achieve, say, broader bandwidth, or you can avoid stretching the pulses and things like that. Of course, modeling is kind of complicated. There's a clever theory about that too, quite interesting mathematics. Yeah, so these, what you see is that this now offers a lot of flexibility, and actually periodically poled nonlinear crystals, they are getting more and more abundant. So if you look in the catalog of, say, Tor Labs, there you find actually a tutorial where they explain the different uses of periodically poled lithium niobate. Yeah, so this is the most frequently used periodically poled crystal. Of course, you see that there are not so many. There's not so much choice there, because it needs to be ferroelectric, which reduces, of course, the available zoo of crystals quite dramatically. So with this, I think we have done enough for phase matching. Next time I will again talk a little bit about crystal symmetry. When we discussed the coupled wave equations, we used the effective nonlinearity, and this I briefly explained it when we discussed the coupled wave equations, but I will discuss it in more detail in the next lecture. See you then, and have a good week. Thank you.